welcome to this problem walkthrough. Today, we'll tackle a fascinating challenge titled Find the longest substring containing vowels in even counts. This problem is both intriguing and practical, as it combines concepts like string manipulation, bitwise operations, and efficient algorithms. Let's dive in and explore how we can solve this step by step. In this problem, we need to find the length of the longest substring in a given string S where all the vowels appear an even number of times. The vowels we care about are a, E, I, O, and U. The string S consists only of lowercase English letters, and its length can range from 1 up to 100,000 characters. Our goal is to return an integer representing the length of the longest substring that meets this condition. To clarify, a vowel count of 0 also qualifies as even since 0 is divisible by 2. Let's start by looking at an example to understand the problem better. In the first example, the input string is LeetCode. The output is 13, and here's why: the longest substring that satisfies the condition is LeetCode. In this substring, we count the occurrences of each vowel, and we find that O appears 0 times, E appears 2 times, I appears 2 times, O appears 2 times, and U appears 0 times. All these counts are even, so the substring qualifies. The length of this substring is 13, which is the result. In the second example, the input string is LeetCode, and the output is 5. Here, the longest substring that meets the condition is leak. Checking the vowel counts for this substring, we find A appears 0 times, E appears 2 times, I appears 0 times, O appears 0 times, and U appears 0 times. Since all vowel counts are even, this substring is valid, and its length is 5, which is the answer. Now consider the third example, where the input string is BC. The output here is 6. This is because the entire string contains no vowels at all. When there are no vowels, their counts are all 0, which is even. Therefore, the entire string is the longest valid substring, and its length is 6. This example highlights that strings with no vowels automatically satisfy the condition, regardless of their length. To summarize, let's look at a few edge cases. If the string contains no vowels, like BCDFG, the result is simply the length of the entire string. If the string consists of a single character that is not a vowel, such as X, the result is 1. On the other hand, if the string is a single vowel, like A, the result is 0 because the vowel appears an odd number of times. Finally, if there are multiple vowels but no substring meets the condition, the result is 0. These constraints and edge cases will help guide us as we implement a solution for this problem. To solve the problem of finding the longest substring where each vowel appears an even number of times, we first explore the brute force approach. The intuition here is straightforward. We examine every possible substring of the given string and check if the counts of vowels A, E, I, O, and U are all even. If they are, we update the maximum length found so far. This involves iterating through all start and end indices of the substrings and calculating the vowel counts for each. While the implementation is simple and easy to understand, it is computationally expensive. Generating all substrings takes quadratic time, and counting vowels for each substring requires another linear pass, leading to an overall time complexity of O(n cubed). Space complexity is minimal at O(1), since no additional data structures are used. However, the inefficiency of this method makes it impractical for larger inputs, especially for strings with substantial lengths. So, we need a more optimized approach to handle this problem effectively. This leads us to consider a solution using bitmasking and prefix sums, which offers significant performance improvements. In the optimized approach, we use bitmasking and prefix sums to reduce the time complexity to O(n). Here's the key insight: the problem of tracking whether each vowel appears an even or odd number of times can be represented as a binary state. Each vowel corresponds to 1 bit in a 5-bit bitmask. For example, if all vowels have even counts, the state is 00000, while if only A has an odd count, the state becomes 00001. The beauty of this approach lies in the observation that if two indices in the string share the same bitmask state, then the substring between these indices must have vowels appearing in even counts, as the changes between them cancel out. Using this principle, we design the algorithm. We initialize a current_state variable to 0 and use a hash map to store the earliest occurrence of each state. As we traverse the string, we update the bitmask for each character. For vowels, we toggle the corresponding bit, while for consonants, the state remains unchanged. If the current state has been seen before, we calculate the length of the substring between the previous index and the current one. We then update the maximum length found so far. This method is highly efficient, with constant space complexity due to the limited number of possible states, only 32 in total. While it may seem less intuitive initially, understanding the bitmask logic unlocks a scalable and elegant solution for this problem. Another potential approach is the sliding window method, which is more intuitive than bitmasking but less efficient overall. In this method, we maintain a dynamic window that tracks the current substring and adjusts its boundaries to enforce the even count condition for vowels. Specifically, we use a hash map to keep a running tally of vowel counts within the window. The right pointer expands the window by including new characters, while the left pointer shrinks it as needed to satisfy the even count requirement. While simpler to grasp conceptually, this method has a worst-case time complexity of O(n squared), as adjusting the window and verifying conditions can take linear time. Space complexity remains O(1), but the quadratic runtime makes this approach less suitable for large inputs. Ultimately, the optimized bitmasking and prefix sum strategy stands out as the preferred solution. It balances efficiency and scalability with its linear time complexity and constant space usage. The key realization is that the problem can be reframed as tracking the parity of vowels using a bitmask and leveraging prefix sums to identify valid substrings. While the sliding window approach is easier to conceptualize, and the brute force method is simplest to implement, only the optimized approach delivers both speed and elegance, making it the most effective choice for tackling this problem at scale. To solve this problem, we need to identify the longest substring in a given string where every vowel, specifically a, e, I, o, and u appears an even number of times. Substrings are simply contiguous sequences of characters, and non-vowel characters don't influence the outcome. To approach this, we can represent the state of vowel counts using a bitmask. This is a compact way to track whether each vowel's count is even or odd. Imagine using a 5-bit binary number, where each bit corresponds to one vowel in the order E, I, O, U. For instance, the bitmask 00000 indicates that all vowels have even counts, while 11,010 would mean that some vowels have odd counts and others have even counts. By updating this bitmask as we process the string, we can reduce the problem to efficiently tracking changes in these states to find the longest valid substring. Now that we understand the problem and the role of the bitmask, let's initialize the necessary components for our algorithm. First, we use a dictionary, called state_map, to store the first occurrence of each bitmask state. This helps us quickly determine the starting point of substrings with balanced vowel counts. Initially, we set state_map to 0-1, since a bitmask of 00000 represents an empty substring. We also need a variable, current_state, to keep track of the bitmask as we iterate through the string. Additionally, we use max_length to store the length of the longest valid substring we find. As we iterate through the string, if a character is a vowel, we update the corresponding bit in the current_state using XOR. For example, encountering in a state of 00000 would toggle the first bit to 00001. If the updated current_state already exists in state_map, we calculate the length of the substring between the first occurrence of this state and the current index. If this length exceeds max_length, we update it. If the state is new, we add it to state_map with the current index. After processing all characters, max_length will hold the result. The key to this algorithm lies in the efficiency of the bitmask representation. By using a single integer to represent the state of vowel counts, we drastically reduce the complexity of checking and comparing states. This allows us to perform these operations in constant time. Another important insight is the reuse of states. When a state reappears as we process the string, it indicates that the substring between the first occurrence of this state and the current index has balanced vowel counts. The state_map dictionary enables this efficient lookup and insertion, and its space usage is minimal, bounded by just 32 possible states, given the 5 vowels. The algorithm operates with a time complexity of O(n), where n is the length of the string, as each character is processed exactly once. The space complexity is O(1), as the dictionary size is constant. This makes the algorithm both time and space efficient. When applying this algorithm, there are a few edge cases to consider. For an empty string, the result is 0 because there are no substrings. If the string contains no vowels, the length of the entire string is returned, as it trivially satisfies the condition. In cases where all vowels occur an odd number of times, the result depends on their distribution in the string. Let's walk through an example with the input LeetCode. We initialize state_map as 0, -1, current_state is 0, and max_length is 0. As we process each character, starting with E, we update the current_state to 00010 and add it to state_map. Non-vowel characters, like L, do not alter the current_state. By the end of the string, the algorithm identifies the longest substring with balanced vowels, which has a length of 13. This is the final output of the algorithm. This implementation solves the problem of finding the longest substring where vowels appear in even counts using a bit masking technique combined with a hash map. Here's a detailed breakdown. 1. Understanding the bit masking approach. Each vowel, a, e, I, o, u, is assigned a unique bit in a 5-bit binary number. For example, a corresponds to the least significant bit, 0th bit, e to the first bit, and so on. The state variable represents the current parity, even/odd, of all 5 vowels. Toggling a bit in the state indicates that the count of that vowel is now odd, or even again. 2. Initialization. A dictionary state_to_index is used to store the first index where each state is encountered. This allows efficient calculation of substring lengths. The initial state is 0, all vowels have even counts, and we associate it with index -1 to account for substrings starting from the beginning of the string. 3. Iterating through the string. For each character in the string, if it is a vowel, the corresponding bit in the state is toggled using the XOR operation. Non-vowel characters do not affect the state. After updating the state, we check if this state has been encountered before. If it has, the length of the substring between the first occurrence of this state and the current index is calculated. If this state has not been seen before, it is added to the dictionary with the current index. 4. Updating the maximum length. The max_length variable is updated to ensure it always holds the length of the longest valid substring found so far. 5. Returning the result. After processing all characters, the max_length is returned as the result. This approach ensures that the algorithm runs in O(n) time, where n is the length of the string. The space complexity is O(1) for the state variable and O(2 to the power of 5) equals O(32) for the hash map, which is effectively constant. This efficiency makes the solution suitable for large input sizes. Here, we start by importing the necessary libraries and defining our solution class with the method findTheLongestSubstring. This method will calculate the length of the longest substring where all vowels appear an even number of times. To achieve this, we use a hash map called state_to_index to store the first occurrence of each unique state. The state variable represents the current bit mask, where each bit corresponds to whether a specific vowel has an odd or even count. Initially, we map state 0 to index -1, signifying that an even count of vowels exists at the start. Next, we initialize maxLength to track the length of the desired substring. As we iterate through the input string, we check each character. If the character is a vowel, we toggle the corresponding bit in the state using XOR operations. For example, a corresponds to bit 0, E to bit 1, and so on. This allows us to efficiently track the parity of each vowel's count as we progress through the string. After updating the state for the current character, we check if this state has been seen before in our state-to-index map. If it has, it means that the substring between the first occurrence of this state and the current index has all vowels in even counts. We calculate the length of this substring and update maxLength if it's greater than the previous value. If the state is new and hasn't been recorded, we store its first occurrence in the map using the current index. This ensures that we always track the earliest position where a state first appeared. Finally, after processing all the characters in the string, we return maxLength as the result. This approach ensures that we efficiently solve the problem in linear time by leveraging bit masking and a hash map to track states. In this problem, we are tasked with finding the length of the longest substring where all vowels a, e, I, o, u appear an even number of times. To solve this, we'll use a bit masking technique that allows us to efficiently track the parity, or evenness, of each vowel as we traverse the string. The key idea is to represent the state of the vowels using a 5-bit binary number, where each bit corresponds to one of the vowels. For example, the 0th bit represents a, the first bit represents e, and so on. If a bit is set to 0, it means the count of that vowel is even. If it's set to 1, the count is odd. During the traversal, we toggle the respective bit whenever we encounter a vowel. By storing the first occurrence of each state in a dictionary, we can quickly calculate the length of substrings where all vowels have even counts. This approach is both efficient and elegant, leveraging the fact that encountering the same state twice implies the vowels between those occurrences are balanced. Let's illustrate the approach with the input string LeetCode. We start by initializing a mapping for the vowels, where a corresponds to bit 0, e to bit 1, and so on. We also initialize a dictionary, state_to_index, to store the first occurrence of each state, starting with state 0 at index -1. The state variable tracks the current bit mask, and max_length keeps track of the longest balanced substring. At index 0, the character is e, a vowel. We toggle the first bit of the state, resulting in state equals 0b10. Since this is a new state, we store it in state_to_index with the current index. At index 1, the character is L, which is not a vowel, so the state remains unchanged. However, we've seen this state before at index 0, so we calculate the substring length as 1 is 0 equals 1 and update max_length. At index 2, the character is again E, so we toggle the first bit back, resulting in state equals 0b00. This state was first seen at index -1, so the substring length is 2, -1, equals 3, and we update max_length accordingly. At index 3, the character T is not a vowel, so the state remains 0b00. Since we've already seen this state at index -1, we calculate the substring length as 3, -1, equals 4 and update max_length to 4. This process continues for each character in the string. Whenever we encounter a vowel, we toggle the corresponding bit in the state, and if the resulting state has been seen before, we calculate the length of the substring between the first occurrence of that state and the current index. At the end of the traversal, the maximum length of a balanced substring for this input is found to be 13. This result demonstrates how efficiently the bit masking approach handles the problem by leveraging the parity of vowels and the dictionary of states. Now, let's look at another example with the input string LeetCode. Here, we start with the same initial setup, the state is 0, and the dictionary contains only the initial state 0 at index -1. At index 0, the character is L, not a vowel, so the state remains 0b0. At index 1, the character E is a vowel, so we toggle the first bit, resulting in state equals 0b10. This is a new state, so we store it with the current index in state_to_index. At index 2, the character is again E, so we toggle the first bit back, returning to state equals 0b00. Since this state was first seen at index -1, the substring length is 2, -1, equals 3, and we update max_length. Continuing this process for the entire string, we find that the longest balanced substring for LeetCode has a length of 6. This example highlights how the same approach can handle different input strings with varying distributions of vowels. Finally, let's consider the input string BC, which contains no vowels. In this case, the state remains 0b0 throughout the entire traversal, as there are no vowels to toggle any bits. The dictionary state_to_index only contains the initial state 0 at index -1. Since the state never changes, the entire string is considered balanced, and the length of the longest balanced substring is simply the length of the string, which is 6. This example demonstrates an edge case where the absence of vowels simplifies the problem. The key takeaways from these examples are that the state variable effectively tracks the parity of vowels, and the dictionary ensures efficient computation by storing only the first occurrence of each state. With a time complexity of O, N, and space complexity limited to at most 32 states, this solution is both optimal and scalable for large inputs. The time complexity of this solution is O, N, where N represents the length of the input string. This is because the algorithm processes the string in a single pass, iterating through each character exactly once. Within this loop, operations such as determining if a character is a vowel, updating the bitmask state, and performing dictionary lookups or updates are all constant time operations, or O1. These small operations do not depend on the size of the input and add no additional overhead. As a result, the dominant factor in the time complexity is the iteration through the string, which is linear, giving us an overall time complexity of O(n). The space complexity of this solution is constant, or O(1), with respect to the size of the input. The reason for this is that the data structures used in the algorithm are fixed in size and do not grow with the input. For instance, the vowels dictionary, which maps the 5 vowels to indices, requires O(1) space. Similarly, the state_to_index dictionary, which keeps track of states using a 5-bit binary representation, can store at most 32 entries, which is constant. Additionally, variables like state and max_length are simple integers that also occupy O(1) space. Since no additional memory is allocated based on the input size, the overall space complexity remains constant. To better understand the efficiency of this solution, we can compare it to a brute force approach. In a naive solution, we would generate all possible substrings of the input string and check each one for even vowel counts. Generating these substrings would take O(n², and for each substring, counting vowel frequencies could take up to O(n). Combining these steps, the overall time complexity of the brute force method becomes O(n³). In contrast, the optimized solution avoids generating substrings by using a state-based approach. It tracks the even or odd counts of vowels using a bitmask and stores the first occurrence of each state in a dictionary. This reduces the time complexity to O(n), as each character is processed once, and dictionary operations, such as lookups and updates, are O(1) on average. This drastically reduces the computational cost while ensuring correctness. Breaking down the time complexity further, we can examine the best, average, and worst cases. In the best-case scenario, where the string contains only consonants, the state remains constant throughout the loop. However, the algorithm still processes every character, resulting in a time complexity of O(n). For the average case, with a random mix of vowels and consonants, the state toggles occasionally as vowels are encountered. Despite this, the processing time remains linear because the algorithm traverses the string once and performs constant time operations. In the worst-case scenario, where every character is a vowel, the state toggles at every step. Even in this case, the dictionary operations remain O(1), and the loop remains linear. Overall, the solution optimally reduces the time complexity from O(n³) in the brute force approach to O(n), while maintaining constant space usage, making it highly efficient and scalable for any input size. When solving this problem, there are some common mistakes to watch out for. First, it's crucial to consider all 5 vowels a, e, I, o, and u. If you forget to track even one vowel, the solution becomes invalid since the condition of even occurrences won't hold. For example, overlooking u could lead to incorrect results even if the other vowels are handled correctly. Next, representing vowel states improperly can cause issues. For instance, using a single counter for all vowels instead of tracking each one individually might seem simpler, but it fails to capture the specific even-odd states required for the solution. Another pitfall is relying on a brute force approach, where you check all possible substrings. This method quickly becomes impractical for larger inputs due to its O(n)3, or worse time complexity. Finally, edge cases like strings without vowels, strings with a single character, or those where all vowels already have even occurrences shouldn't be overlooked. For example, with inputs like XYZ or AEIOUEIOU, your solution should still return correct results without errors. Now, another mistake to avoid is skipping modular arithmetic when checking even or odd counts. Using simple modular operations like count%2 is not only faster but also reduces the risk of logical errors compared to manually implementing even-odd checks. Moving on to interview-related insights, this problem is a great example of applying bitmasking and prefix sums, which are common patterns in substring and subarray problems. By representing the state of the vowels using a fixed-size bitmask where each bit corresponds to a vowel, you can efficiently track and compare states. The optimal solution involves using a hash map to store the earliest occurrence of each state. Whenever the same state appears again, the substring between these occurrences has vowels in even counts, allowing you to calculate its length. State compression using a 5-bit integer, like 00000 for all vowels even or 10,101 for a mix of even and odd, keeps the solution space-efficient while enabling fast lookups. However, while this optimal approach runs in time and space, it might require extra effort during debugging due to the complexity of bit masking. This problem also connects to several related problems that use similar techniques. For example, in LeetCode 560, subarray sum equals k, you use a prefix sum approach to find subarrays that sum to a target value. The problem we're discussing here, LeetCode 1371, also relies on prefix sums but applies them to track even and odd counts of vowels. Another related problem is LeetCode 523, continuous subarray sum, which involves modular arithmetic and prefix sums to check for subarrays divisible by a specific number. Similarly, LeetCode 974, subarray sums divisible by k, uses modular arithmetic to track states and solve the problem. These problems share overlapping concepts, so mastering one can help you recognize patterns and apply them in others. Finally, let's look at some alternative approaches to solving this problem. The brute force approach involves checking all possible substrings, counting the vowels in each, and verifying whether their counts are even. While this method is straightforward, its in superscript 3, time complexity makes it unsuitable for larger inputs. A better option is the sliding window method, where you dynamically adjust the window size and track vowel counts as you move through the string. This can achieve time complexity in the best case, but it requires careful implementation to handle edge cases correctly. The most efficient approach is the bit mask combined with prefix sums. Here, you represent the state of vowels using a bit mask and use a hash map to store prefix sums for quick lookups. This method runs in time and is space efficient, but it does require familiarity with bit masking techniques to implement correctly. Each approach has its trade-offs, so choosing the right one depends on the problem's constraints and your comfort level with these techniques. Great job making it to the end. In this problem, we learned how to use bit masking and prefix states to solve a tricky substring challenge efficiently. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and stay tuned for more coding tips and techniques. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!